Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about entropy and probability. We're going to define what entropy is, finally. So let's jump right on in. Okay, so when we introduced the definition of entropy, we said, well, let me actually write all of this out. So when we introduced that ds is equal to dq reversible over t, which was our definition of the differential element, essentially the definition of entropy, we didn't give a structural model. We did not require, we did not require a structural model for the system in order to work with entropy. In order to work with this state function entropy or describe its behavior. In fact, we didn't even need to know what entropy was. We had these mathematical descriptions, and then we had these constraints of temperature, pressure, volume, and we saw how entropy behaved. We were able to derive and calculate numerical values for it. The only thing that we really did was casually refer to it as a measure of the disorder or randomness of the system. And I still think, in my personal opinion, that disorder and randomness is actually a great way of thinking about entropy. But now what we're going to do is we're actually going to define what we mean when we say disorder and randomness. We're going to quantify it. We're going to come up with some numerical way of explaining what is this disorder or randomness. Okay, so when I use the words disorder and randomness, what I'm actually talking about is something called a distribution. So that's it. When we talk about disorder or randomness, we're talking about a distribution. And in this case, it's going to be the distribution of particles. So again, we didn't require a structural model. We didn't care what a particular system was made of, whether it was particles, chairs, whatever. It could be made of absolutely anything. There was this behavior that it represented. This is our empirical observation, and we were able to use mathematics to derive to describe different ways of how this thing behaves. Now we're going to give it a structural model. So here is our structural model. Actually, you know what I'm going to do? I'm going to go ahead and do this in blue, I think. Okay, so our structural model. It's exactly what you think it is. A system is composed of a very large number of particles. That's it. Of a very large number of particles. And those particles could be molecules, they could be atoms, they could be ions, whatever it is that you happen to be discussing in that particular problem. So I'll write molecules, atoms, and ions. Okay, now let's say some things about these particles. Now, these particles have various energies. These particles. So the best way to think about this is to think about just a gas, a collection of gas. Like the kinetic theory. Basically, it's just a bunch of particles in a fixed space that are bouncing into each other and bouncing off the walls. That's a system. So these particles have various energies. In other words, not each particle is flying around at the same speed. There are some that are going faster, some that are going slower. There is a large number of them that have the same energy. There are others that also have the same energy, so there might be 10 million of them that are traveling at 500 kilometers per hour. There might be 20 million of them that are traveling at 550 kilometers per hour. So they're distributed. All the energy is distributed among the different numbers of particles. So these particles have various energies, and there is a distribution. distribution of the total energy of the system, the U, of the total energy of the system, which is U, first law, over the various particles. That's it. The total energy of the system is made up of the sum of all the individual energies of the particles. That's it. That's all it is. If a system has 100 joules of energy, well, those 100 joules are going to be distributed among the different particles in different ways. Maybe 2 particles might have one energy, 2 particles might have another energy, 15 particles might have another energy, all the different energies, that's the distribution. Okay, in other words, exactly what we just said. In other words, n sub 1 particles have energy E sub 1. N sub 2 particles have energy E sub 2, and so on. That's it. Now, the number of particles, the total number of particles, so n sub 1 plus n sub 2 plus n sub 3 and so on have to equal n, which is the total number of particles in the system. That's it. So if I have 100 particles in the system, n sub 1 might be 10, n sub 2 might be 20, n sub 3 might be 70. 70 plus 20 plus 10 equals 100, the total number of particles. So that is one of our constraints. Now, the number of particles with energy 1 plus the number of particles plus energy 2 plus the number of particles with energy 3 and so on onto the number of particles n sub I with energy sub I, that has to equal the total energy of the system. So when I add all these energies, the maximum energy that I can have is U, the total energy of the system. That's the second constraint. That's it. Nothing strange happening here. The system has a certain energy. Our system is made up of a bunch of particles. We're distributing this energy over the bunch of particles. That's all. Okay. Now, the next part of the structural model is these particles. So the first one is these particles have energy. Now, these particles occupy space. These particles occupy space. In other words, volume. Now, I'm not saying that they themselves have volume. I'm saying that they are contained in a volume. There is some fixed volume that they are in. So whatever that volume is, they're occupying that space. Okay. Now, there is a distribution. Distribution of these particles. This is the most intuitively clear one. Of these particles over the volume available. Over the volume available. So we have these 100 particles, and let's say we have a 1-liter flask. I dump these 100 particles in the 1-liter flask. Well, the particles are going to arrange themselves in all kinds of different ways. Maybe, this particle is here, this particle is there, all the 100 all over the place. There are a bunch of different ways that these particles can distribute themselves in that 1-liter flask. That's the volume distribution. So they are going to arrange themselves in a volume up to the maximum capacity of that volume. That's it. You know this intuitively.